Good morning children, welcome to Sri Ramanja Vidya Mandir, a temple for learning. Children, in previous class we discussed about magnetic field due to a current carrying wire. Means if we take any wire, current carrying wire, around that wire how that magnetic field will be creating, and the direction also we have seen children. That magnetic field will be inwards or outwards, symbol for inwards, symbol for outwards, and we have seen an important law, that is Biot-Savart law, by using which we can find the magnitude of magnetic field due to a current carrying wire. Okay children, so in the last class we discussed about what? Magnetic field due to current carrying wire. See, remember children, here we are taking straight conductor in the sense straight conductor. We are not considering this full length children. This full length, okay, we are, while writing the formula in the previous class, we are not considering, while deriving the formula, we are not considering full length. We are taking only small part of this. Only small part we are taking, that is dl, small part. Due to that small part, how much magnetic field will be created, that one we will consider. Okay, suppose this is the small part children, and here some point P, and from here to here the distance is r. Okay, now from here to here, from dl to r, there will be what children? Angle theta. So here the important thing is children, the wire always it won't be straight. Always it won't be straight. Sometimes it will be spherical. That wire it will be wounded like a circle. Sometimes we will consider two wires. Sometimes that wire will be infinity wire without any specific length. Sometimes it can be semi-infinite. Means one end will be infinite, another one will have some limit. Different conditions are there. Okay, so children, the law what I am going to discuss now is for a current carrying wire, okay, which is straight conductor. Okay, see children, Biot-Savart law. Children, I already explained in the previous lecture. So this is the formula for finding the magnitude of the specific magnetic field, that is I dl by sin theta by r square mu naught by 4 pi. See children, here important thing is, in the last lecture I discussed about magnitude, but we did not say about, we haven't bothered about that direction. Whether the magnetic field at a point P, this is point P children here, whether the magnetic field is inwards or outwards, we need to find. In the last class we derived this one, means we have seen this dB equal to mu naught by 4 pi ideal sin theta by r square. Okay, now what I am going to do is, I will show how to find the direction. Okay children, whether that magnetic field is entering inside the page or outside the page. Suppose this is the plane children. Okay, for this plane, that magnetic field is inwards or outwards. Inwards or outwards. Okay, for inwards this is the symbol children, cross. For outwards, dot. Okay, clear? See, remember children, formula is very important. Okay, see children, in this specific notation here ds is there, but instead of s I am taking dl. Okay, so dl, sorry, dB is equal to I dl sin theta. Okay, multiplying with what children? Sin theta by r square, multiplying with the constant mu naught by 4 pi. Mu naught by 4 pi. Okay, see children, here important thing is the dl whatever we are considering, it is this dl also a vector, dl also having some direction. Okay, it is also some vector, as well as that r bar we are taking, right, the distance between dl and p, that is also a vector quantity. That's why I'm keeping bar here. Okay, and from dl to r bar there is some angle that is nothing but theta. Okay, okay children. So in vector algebra, see children, vector algebra in the sense it is not a very complex thing. Suppose if we are checking our mass like 2 kg 3 kg, suppose if we take mass, how do we measure 2 kg 3 kg like that? Here there is no direction we are not mentioning, whether it is upwards, downwards or something, just a magnitude, number and unit. Okay, so this is called what? Scalar. So directly we can add 2 plus 3, but that is what children? Scalar. If we take some velocity, it will be like minus 3 meter per second and plus 2 meter per second, minus plus. Okay children, if we take velocity is a vector quantity which has some specific direction. This minus is nothing but direction only children, backwards, frontwards. See, for 2 kg 3 kg we won't mention any direction because it is independent of direction. But velocity does matter. Displacement, velocity, force, acceleration, all these are having what? Directions, specific directions. So whenever there is specific direction, we need to follow vector algebra. Okay, what is that children? Vector algebra. Vector algebra, we have one important thing children, that is cross product. Cross product is nothing but, suppose if we have two vectors are there children, a bar and b bar. If you want to find resultant, if you product a bar and b bar, if you do product, but which product? Cross. Then what is the formula children? AB sin theta. Okay children, so for scalars we no need to follow all those notations, sin theta and all. Directly we can add 2 plus 3, 2 into 3 product, 2 into 3 and all 6. Well, coming to the vector quantities, whenever we are dealing with vector, we need to keep in our mind, we need to mention direction also. Okay children, so the thing what I am saying is, here dl bar is also a vector, r bar also a vector. So for these two, what I am doing, I am taking cross product. Cross product means dl bar cross r bar. See children, a bar cross b bar, ab sin theta. Similarly, dl bar cross r bar, dlr sin theta. Okay children, okay, clear? dl r sin theta. Okay children, so here the important thing is, we need to find direction. We need to find what? Direction. See children, this is what? Inward. In previous lecture I explained clearly regarding this. Dot, which is nothing but outward. Inward in the sense that corresponding vector, that corresponding magnetic field is inside, it is going inside. Okay, Suppose consider some bottle cap, children, bottle cap. Okay. When you are rotating the bottle cap, how that bottle cap will go? Inside it will go. When you are rotating in anti-clockwise, outside it will come. Clear now? Means when you are rotating the bottle cap in clockwise direction, when you are rotating in clockwise direction, how the resultant is there? Inside. When you are moving this, rotating that one in anti-clockwise direction, if you rotate that cap in anti-clockwise direction, then it will come outward. Okay, children? So this one, basing on vector notations only, we are able to say, children. Vector is very, very important. Okay, vector. So specifically regarding magnetic field, in order to determine the magnetic field direction at some point P. Okay, at this point P, we know that some magnetic field will be created. See, children, this is, let us consider some wire, some copper wire, and through this wire some current is flowing, some current I. I already said whenever there is flow of current, what will they around this one? Some magnetic field will be created. What I am saying means, suppose I consider some point P here. Okay, this magnetic field won't restrict only here, children. It continuously spread. Okay, now this magnetic field will be induced near P also. That magnetic field which is created due to this current carrying conductor, it will touch this P point. Near P I kept some charge. Here some charge is there. Okay, so near this charge also some magnetic field will be created. How much magnetic field will be created? By using this formula we can find. That's fine. Magnitude we will get some numerical number. But what about direction? That magnetic field at P, suppose this is point P, children, some point P. It is going inside or it is coming outside. Near this point P, this magnetic field whatever is there, it is going inside or coming outside. Suppose this is point P. That magnetic field going inside or coming outside. We need to find. Okay. So by using this Maxwell corkscrew rule, we can find. What is this, children? Maxwell's corkscrew rule. Once see, children, if you are rotating screw in clockwise direction, once observe the direction of current is downwards. See, children, normally screw, if you rotate in clockwise, it will go down, right? So that rotation indicates magnetic field. The direction of screw indicates current. Rotation indicates what? Direction of magnetic field, and direction, that resultant indicates what? That movement indicates what? Direction of current. Okay. Similarly, if it is in anti-clockwise direction, anti-clockwise, we are rotating the screw in anti-clockwise direction. Now screw will come upwards, means the movement is upward, means current direction is up. Clear, children? I am taking help of that one. Okay. So see, children, now this one is DL bar, this one is R bar, and this one is point P, and this one is some theta. Suppose if I rotate in clockwise direction, suppose if I rotate this one in clockwise direction, DL to R bar, DL bar cross R bar. Okay, children, let us consider DL bar is there. Okay, DL bar and R bar. DL bar, this one DL bar, this one is R bar. Suppose if I rotate like this, V bar to R bar. What is that direction, children? Clockwise direction, right? DL R bar, rotating like this. Okay. Whenever I am rotating in clockwise direction, how that magnetic field will be induced, children? Inwards only, no. Very, very simple topic. When you are rotating like this, magnetic, see, DL to R, means clockwise direction, clockwise, then magnetic field will be inwards. Okay children, inwards. Okay. See children, suppose if this is not straight wire, if it is a circle, if wire is some circle and this one is axis of the circle, current carrying wire only children, it was kept in a shape of circle. This one is what? Axis. Along the axis at some point P, I can see some point P is there, okay, which is at a distance of x. And the radius of this circle is what children? R. Okay. See children, like I took dl, here also I am taking some dl. Clear children? This wire is carrying some current. Some current is there actually. Okay, this one also. Current is there. dl this one. Okay. Now due to this dl, what's going to happen? Some magnetic field will be induced. Let us consider that distance as r bar only. This is arrangement children. This is what? Some arrangement. Along the axis I kept that P. Clear? So what will be the magnetic field at point P due to this circular current carrying wire? Okay. Children, one more point. Suppose, come back here once. See children, suppose just here this is wire and we are taking this one as dl, and here this is point P and this is some theta. Now suppose if I move this point here, okay, where I kept this point children? Along the wire. Along the wire. Then here how this diagram will be children? This one is dl and this one is point P. P instead here I am just moving to here children. Now what is the angle? Angle will be what now? No angle, right? So theta is equal to 0. Okay. When P is along the current carrying wire, P is along current carrying wire. P is along the current carrying wire. Then theta is what children? 0. If theta is 0, once see the formula. dB equal to ideal sine theta by r square into mu naught by 4 pi. Children, once see here, theta 0. If theta is 0, sine theta also 0 only, no. Sine 0 is 0. If the sine theta is 0, then what about dB? dB also 0, right? Clear? So if whenever theta is 0, see children, very very important point this one. dB is equal to mu naught by 4 pi ideal sine theta by r square, right? Suppose what I am saying is, if theta is 0, then obviously what? Sine theta will be 0, right? Sine 0 is 0. Whenever the sine theta itself is 0, then what about dB children? dB also 0. Because here sine theta 0 means this entire term becomes 0 and dB also 0. So no magnetic field. Suppose if that theta is 90. If theta is what? 90 degrees. If theta is 90. See children, objective bits point of view, these points are very very important. Then sine 90 will be how much children? Sine 90 is 1. Then what about dB children? dB is equal to mu naught by 4 pi I dl into sine 90, right? Means 1. Sine 90 we got 1 by r square. So this is what children? Maximum value. This value of dB whatever we got, this is nothing but what? Maximum value. Okay. So whenever theta is 90, what it sends? If this is dl, this is P, which is perpendicular. dl bar and point P are perpendicular to each other. In that case, dB will be what? Maximum. If this one is dl and this is point P, means what? dl and P are parallel. Whenever these two are in parallel, dB is what children? 0. Very very important point. Very very important. Okay children. So point P in order to must be placed perpendicular to the wire so that we can get maximum magnetic field. Yeah, see children, this is the case I am talking about. If this is the wire, this is the wire children, this is point P and this one is distance x, this one is r, this one is dl. From dl to P the distance is r children and radius of the circle is capital R, and from center of the circle to the point P the distance is what? X. Now how much amount of P is induced? How much amount of magnetic field is induced at P? How much amount of magnetic field is induced at P? Simple children, this is the formula, direct formula I am saying. Mu naught I by 4 pi 2 pi r square, B is equal to mu naught I by 4 pi 2 pi r square by x square plus r square whole power 3 by 2. This is direct formula children. How much magnetic field is created here? This is the formula. Mu naught I by 4 pi into 2 pi r square by x square plus r square whole power 3 by 2. See, this derivation includes both integrations and differentiations, so it may be somewhat complicated. So directly it is better to go through this formula in your next class. I will discuss about that. Means you need to be enough with derivations, which will be means now at your school stage there won't be any integrations and derivations children. So first I will say the basics, how to do differentiation and how to do integration, and then I will explain this specific formula. Okay children, derivation. So this is the formula children for up to objective level. If you can remember this formula, that's more than enough, but you need to identify at what distance P is placed, that is x. At what distance that object is placed, that is x. Okay, and radius of circle is what? Capital R. Okay, in question I will be given to you children. Current, or how much current is passing through that wire, I is given to you, will be given, and capital R also they will give, radius of the circle, and within how much distance point P is placed, that one also will be given for you. Okay, that is x value also given to you. No worry. Just to find, just you have to do some mathematical simplification, that's it. Okay, here mu naught I by 4 pi is nothing but what? 10 power minus 7. Multiplying with corresponding values, you will get your answer. Okay. Yeah, see children, suppose if you are placing north pole and north pole. Okay. This is the direction of magnetic field lines. And at this middle point there is no magnetic field. This point is called a neutral point. Neutral point. Okay children, that point is nothing but what? Neutral point. See, why I am saying regarding neutral point means children, there won't be any magnetic field at neutral point. If there is no magnetic field, there won't be any force also. No magnetic field in the sense there is no force. Okay, children. Next. Yeah, children, this one is I already explained, followed by the screw rule. This is the important, that is right hand thumb rule. Fingers represent magnetic field and thumb represents current direction, or else reverse. If fingers represent current direction, thumb represents magnetic field. Okay. Yeah, see children here. Left hand rule. Left hand rule. Okay. See children, I will explain this one with an example. Suppose this is direction of magnetic field. And I kept some charge here. Here some charge is placed. And that charge is moving, which is nothing but current direction only, children, in this direction. In this corresponding magnetic field. Magnetic field into the page. Magnetic field into. Okay, that charge is moving like this. Into, and this is the direction of charge. In which direction? Force is acted on that specific charge. In which direction there will be force acting on the charge, children. That is the thing we need to find now. By using left hand rule we can find. See children, let us take 3 fingers perpendicular from left hand. Thumb represents what? Direction of force. Okay. 4 finger represents direction of current, and middle finger represents direction of magnetic field. Okay children, sorry. Thumb represents force. Forefinger represents magnetic field, and middle finger represents current, children. Middle finger represents current, forefinger represents magnetic field, and thumb represents direction of force. Okay. Children, see here, magnetic force is inside, magnetic field is inside. Okay. And current direction is left side. Thumb represents, thumb showing upwards, no children. So the direction of force is up. Okay, simple children. This is formula, children, how much force is acting. Okay. And here we can write this one like this also. F is equal to Q into B bar V bar cross B bar. V bar cross B bar. See children, cross product. Extension for this cross product is BV sin theta. Same, both are similar. V represents what, children? Current direction. B represents magnetic field direction. And Q is the charge. And F represents how much force is acting on that. Here also same thing, children. If this theta is 0. If theta is 0. If theta is 0, then sin theta will be 0, children. Whenever sin theta is 0, force acting on the particle also 0. Next, if theta is 90, sin 90 will be 1, children. And F is nothing but what? BQV. Okay. So this is nothing but what, children? Like I said in previous case, maximum value. When you will get maximum value? When B and V are perpendicular to each other. Magnetic field and current direction is what? Perpendicular to each other. Magnetic field B and direction of charge V both should be perpendicular. Then you will get maximum force. See children, one rule is there actually. That is right hand palm. By using right hand palm. Fingers represents magnetic field. Thumb represents the direction of V, direction of charge. Fingers represent B. Thumb represents V. This palm represents direction of force. See children? Fingers. See magnetic field inside, right? So fingers I should keep inside. inside I kept. V is that direction. So I am keeping thumb also in that same direction. Now palm is showing upwards. So magnetic field will be up. Like this also we can do. Either left hand rule or right hand palm rule. Clear, children? This is very simple. Just you will keep the direction, whether it is inwards or outwards. Whether if it is inwards, you will keep fingers inside. In which direction V is there, in that direction you will twist this V, thumb, and palm shows magnetic field, force. How much force is acting. Okay, children, very simple. Yeah, see, children, suppose if two wires are there. Okay, children, let us consider now two infinite parallel current carrying conductors parallel current carrying wires. Okay, here infinite wires, children, two parallel infinite wires, and current I is moving, okay, through the two conductors, equal amount of current flowing, children, in same direction. Direction if current is same. Okay, so we know that whenever there is flow of current, then there will be production of magnetic field. So due to this first conductor, there will be magnetic field, children. That magnetic field affects the second conductor also. Okay, once observe, children, near the second conductor, this magnetic field is entering. Near the second conductor, magnetic field entering, and current is moving. Okay, magnetic field is entering inside near second conductor. Okay, and the current is, see, children, this is current direction, and inside magnetic field is entering inwards. Clear? So take right hand, stretch your fingers along magnetic field, children, that is inwards, and thumb along the direction of current upwards. Now our palm indicates the direction of force, that is towards first conductor. Similarly, due to second conductor also, there will be production of what? Force. Now this force will be in opposite direction, obviously. So this is force in first one, children. This is force in second conductor. So force in first conductor and this is force in second conductor. Once observe, children, both are in opposite direction. Okay, so we can write like this. So it is having a property of attraction, children. Okay, see, if you take here, if you observe here, send this F2 here, children, it becomes what? F1 plus F2, net force is equal to 0. Means what here? Forces are adding here. Okay, means the two wires come closer. Two wires are getting closer. See, opposite direction, two forces are acting, so they are getting closer. Means they attract each other. They attract. When they will attract? When current direction is same. In both wires, if current direction is same, then the forces makes the conductors to move together. Means attractive nature will develop between the two wires or between two conductors. Okay. See, children, now suppose infinity wire, okay, and now the current is in opposite direction, children. Flow of current is in opposite direction. So see, children, conductor 1 and conductor 2. First conductor and second. See, due to first conductor, the second conductor also receiving magnetic field which is inwards. Like previous case what we dealt, force will be towards, force is acting towards first conductor, that is force in second conductor F2. Okay, children. Now Once observe magnetic field in second one. See children, use right hand thumb rule, current is downwards. So magnetic field will be inwards. This is conductor, current down, fingers representing the direction of magnetic field, which means in this direction. Okay children, so for the first conductor what happened here, once observe carefully. This one I am enlarging. This is conductor, okay, and this is the direction of magnetic field. Means magnetic field is entering. In this current direction is upwards. Okay, magnetic field entering children, current direction is upwards. Magnetic field, once observe, magnetic field, use right hand palm rule children. See, at this point magnetic field is entering, okay, current direction is upwards. Magnetic field entering, current direction, magnetic field entering, current direction upwards, means it is away from the first conductor. The force is acting away from the first conductor. That is force in first conductor. So this is F1 children. Once observe now in the second case, this is direction of F1 and this is direction of F2. Okay children, means what? This is moving, this is also moving. Two conductors are moving. Okay, there is no attraction. Attraction in the sense both should come together. Now what happened? Both are moving away from each other. Clear children? So here which type of nature user to develop means repulsive nature. Repulsive forces user to exert now. Whenever the current carrying wires are having currents in two wires are carrying current in same direction. Current is in same direction in both conductors. Next, current in opposite direction. When current is in same direction, two conductors will attract children. Okay, when currents are in opposite direction, the two conductors will repulse. They repel from each other. Okay children, very very important. And yeah, see children, this is see children, right hand palm represents force, fingers represents B, and thumb indicates current. Till now I used this law only. Okay, this is just a diagrammatic representation. Yeah, see children, thumb indicating force. Okay, Fleming's right hand rule, right hand. I explained earlier left hand, now it is right hand. See children, I drawn diagrams. Okay, direction of force, thumb indicates direction of force, forefinger indicates direction of current, middle finger indicates direction of magnetic field. Clear? Yeah, see children, here this is working of DC motor actually. This is the direction of magnetic field B. This is B, direction of magnetic field which is moving from north to south. Always flux lines used to move from north to south only, no children. Next, this is the direction of current. Current direction once observe children, red color. This is current direction. Okay, magnetic field, current direction. Means force is away, which means in this case force is upward direction children. Okay, yeah, this is current direction children I, this is magnetic field B, and this, yeah, we can consider this arrow as force direction children, means upwards, just representing upward direction. Okay, see children, this is B, magnetic force, magnetic field, this is I, B, I. Okay, Now how that force will come? Upwards. This is B, this is I. Now thumb representing force upwards. Okay. So due to this force, that magnetic motor gets rotation, children, and that motor used to make rotations. See, children, this is solenoid. Okay. See, children, solenoid is nothing but, suppose we can take any non-conducting material, non-conducting in the sense which should not allow current through. Suppose if you consider this marker, this is made up of fiber or plastic, so it won't conduct any current through it. Now we have to take some copper wire and we need to wound. That whole arrangement becomes what? Solenoid. Inside the solenoid, see, children, this is direction of current. Direction of current. Okay, children. So on it continues up to here. This is what? Direction of current. Like this, the current is moving. Okay. And once observe magnetic field lines, children. These are magnetic field lines, blue color. So here we can use right hand palm rule. Once observe, children, the current direction is inward. See, this is the wire, and like this the current is moving. Means this direction represents direction of magnetic field. This represents what? Direction of magnetic field. Okay, children. So once observe, children, here this model actually we use, means this is just a model, children. We use this model while constructing transformers. Okay, children, while constructing the transformers and in small alarm setup alarms and like doorbell, in everything we will employ this one. Okay, solenoid. Suppose if we bend that solenoid, if we bend this solenoid, it becomes toroid. Okay, children, it becomes what? Toroid. Same this one, children. If you bend like this, it becomes toroid, and here also magnetic flux will be there. Okay, so what is the magnetic field? How much will be that magnetic field, children? B is equal to mu dot Ni by 2 pi r. This is formula, children. Formula we need to remember. Where N represents, by using Ampere circuit law, we can derive this one, which includes integration and differentiation. So directly I am giving this one. See, children, number of turns and magnetic flux both are proportion. B proportional to N. If number of turns more increases, B also increases. If number of turns are 2, magnetic flux also increases 2 times. If number of turns increases by 3 times, magnetic flux also increases by 3 times. Okay, children. So similarly here also, for this one also the magnet formula is there. How much it is? B is equal to mu naught N into I. Okay. See, children, regarding mu naught I explained in previous slides, where N is these number of turns, that is again proportional to what? B. And where I is current, children, how much current is flowing through the wire, that's it. Okay, children, so that's all for this today's session. Let's meet in the next lecture with an interesting topic. Okay, extension for this. Okay, children, thank you and have a